Hi everyone. Today our topic is the volume of prisms and cylinders in Cavalieri's principle. We'll talk a little bit more about what Cavalieri's principle is later. Our objective for today is that students will be able to identify prisms and cylinders with the same volume by using Cavalieri's principle. So we're going to be looking at pairs of cylinders and prisms and seeing whether or not their volume is the same by using this new tool that we're about to learn. So one application that I came up for this is that two suitcases may look different, but take up the same amount of space, right? One might be shorter and wider, while the other one's smaller and taller, right? But the volume might be the same. So this is something that can help you make good buying decisions when you're looking at, say, furniture for your house or suitcases like I mentioned, or even backpacks and purses. So right now you can go ahead, pause this video, and write down one more application where you could use comparing volumes in real life. All right, so we're going to take a look at our notes now. These first couple of questions are actually questions that you are capable of answering by yourself. So this first question says, the bases of the following triangular prism T and rectangular prism R lie in the same plane. So that means that these two objects here, this triangular prism and this rectangular prism, the way that they're lined up is like they're sitting on a table right next to each other, right? They're on the same level. They start at the same height. A plane that is parallel to the bases and also a distance 3 from the bottom base intersects both solids and creates cross sections T prime and R prime. So what that means is that this blue cross section here and this blue cross section here, both of those cross sections are also at the same level, right? They're 3 above the table. So our first one asks us to find the area of T prime. So T prime is this shape right here, right? It's a cross section of our prism. And since this plane is parallel to both of the bases, we know that this cross section has the same area as the base on the bottom or as the base on the top. All of them are the same. So for this one, you're going to use your area formula, right? The area of the triangle, we're not finding volume, we're just finding area. Area is going to be 1/2 the base times the height of the triangle, right? So you can go ahead, pause this video now, and you can figure out what the area is. I'm not actually going to go over this area problem. I'm going to trust that you are able to do that one on your own. Let's move down to part B, which asks us to find the area of R prime, which is this shape right here. And keep in mind that that's the same as this base, which is the same as this base, right? Because these are parallel, they are all identical. So this is a rectangle. Finding the area of a rectangle, we're just going to do base times height. Again, you can go ahead, pause this video and work on that. Thanks for working on that. Now we're going to find the volume of the triangular prism and the volume of the rectangular prism. And the way we'll do that is by using our volume formula. Volume is equal to area of the base times the height. Now you know the area of the base because you found it out in part A and B, and you know the height of each of these is 5. So you can go ahead, find the volume of T, which is the triangular prism, and the volume of R, which is the rectangular prism. Okay, so now we're looking at part E, and part E is a thinking question. So this asks, if a height other than 3 were chosen for the cross-section, would the cross-sectional area of either solid change? So it's asking if we moved that blue plane up or down, would that cross-sectional area change? So let's go back over, let's look here. here are our shapes again. So if instead of being at a height of 3, we moved this down so that it were at a height of 2, right? So if we moved this triangle down here, would this new triangle have the same area or a different area, and why? That's what this question is asking. So again, this is just a thinking question, so you can go ahead, pause this, and fill in part E. Thanks for thinking about that. Now let's move down to our discussion section. This discussion section starts with giving us 3 figures, right? We've got the red figure, the green figure, and the blue figure. Now all of these are very strange, right? They're not our typical rectangles or triangles that we have formulas for. So our first question is saying, which shape do you believe is the largest? We're going to talk a lot about this in the next couple minutes, but before we do that, I'd like you to write here, just write a little bit about which one do you think is biggest, the red one, the green one, or the blue one, and why. Thanks for thinking about that. Now, we're going to look down here at these 2 examples. And while I'm talking about this, I want you to think about whether you are going to change your mind about which one you think is bigger, okay? So think about what did you write down and whether what I'm about to say will change your mind. So example 1 and 2 here are showing us that at specific heights, right? So this height is at, it looks like level 4. So if I go up 4 dashed lines, what this first example is telling me is that this distance on the red one, and this distance on the green one, and this distance on the blue one, those are equal. They're all the same size. So that means that these shapes are the same width at that specific height. Now example 2 is also saying that at this higher height, right, this distance is the same as this distance on the green, which is the same as this distance on the blue. And from this observation, we can also think about the fact that this distance is the same as this distance, which is the same as this one. So what I'm telling you is that at any specific height on these pictures, all of the distances are the same on each of those 3. So does that change your mind at all about which shape you believe is the largest, the red one, the green one, or the blue one, if they're always the same width? I'd like you to think about that. And if you would like to go up and change your answer or add something to your answer, you can go ahead and do that now. Now, some of you probably figured this out as I was talking about those previous shapes, but this is something called the principle of parallel slices in the plane. This is basically saying if 2 planar figures of equal altitude have identical cross-sectional lengths at each height, then the regions of the figures have the same area, okay? So I'm going to break that down piece by piece. So if 2 planar figures are just shapes. If 2 shapes of equal altitude, so they have the same height, have identical cross-sectional lengths at each height, so are the same width everywhere, then the regions have the same area. So essentially what I'm saying is, if I have shapes that at each height have the same width, then those figures have the same area. So you can see down here at the bottom of our screen that if I break these up into little teeny tiny slices and I cut them into these little pieces, all I'm doing is shifting those pieces around. Let's take a look at what that might look like with a rectangle and turning it into a parallelogram. Let's think about these two rectangles. They're the same height and the same width, so they are congruent and they have the same area. Now, do they still have the same area if I move the strips of this rectangle so I have more of a blocky parallelogram rather than a rectangle? Of course, I didn't add any area or take any away. I just rearranged it. I could shift these into any strange shape and the area would stay the same. If I were to do this with any shape, cut it into small strips and shift them back and forth, the area would still stay the same. So now that we've seen that demonstrated with pieces of paper, which hopefully really helped you visualize this well, let's look at our example here. So the definition of a parallelogram is a quadrilateral with two pairs of parallel sides. So our question says, here's a rectangle. What would the dimensions of a parallelogram with equal area be, right? So the dimensions of this rectangle are 9 by 4, right? So that means that our area, 9 times 4, is 36 centimeters squared. So what this question is asking us is, what would the dimensions of a parallelogram be where our area would also be 36? Now, there are several parallelograms that fit this. But if I think about my principle of parallel slices in the plane, I know that if I take something that's the same height and I just shift all of my pieces, right? So if I have something that still has a height of 4 and my width is still 9 everywhere, right? Even if I shift it over, if I just take my pieces and I shift them a little bit, my area is still 36, right? So the dimensions of this parallelogram, which basically means what are the values that we know, right? We know that for the area of a parallelogram, we usually need to have the base and the height. So we know that the base will be 9, right? And the height will be 4. And those are the dimensions that we need to have a parallelogram of equal area. Now, last week we talked quite a bit about the idea that area and volume are very similar ideas. Volume is really an expansion of area. So we can take what this principle of parallel slices was telling us about area, and we can shift that into what it might tell us about volume. And this is what we call Cavalieri's principle. So this principle says, given two solids that are included between two parallel planes, if every plane parallel to the two planes intersects both solids in cross sections of equal area, then the volumes of the two solids are equal. What does that actually mean? So what this means for us is that if instead of having those strips of paper, right, that we're shifting, if we have slices of something stacked on top of each other, and if all of our slices are the same, if we shift those around, that shifted shape still has the same volume. So let's break this down. Given two solids that are included between two parallel planes. Okay, so that's just a 3D shape with the same height. Okay, that's all it's saying. If I have two 3D shapes that have the same height, if every plane parallel to two planes intersects both solids in cross sections of equal area, so if we have the same cross-sectional area everywhere, this is very similar to the same width everywhere when we were talking about area, right? So if we have the same cross-sectional area everywhere, then the volumes of the two solids are equal. So if I have the same height and the same cross-sectional areas, then the two volumes are also the same. So for example, if we looked at these two shapes, if we knew some more about these dimensions, we're not going to do this specific example, we're going to do an additional example. But if we knew the dimensions of these two shapes, and if we knew that this plane P, that this area was the same as this area, and if I made another plane, if this area is the same as this area, and if this area is the same as this area, then these two volumes are the same. Let's take a look at a quick manipulative example of this using pennies. Now let's look at the stack of pennies. Because the stack is made of only pennies, the area is the same anywhere. If I shift these pennies so that I no longer have a right cylinder and I now have a slanted shape, the volume is still the same. In fact, if I had triangular coins that had the same area as the pennies do, but they were still the same height, my shape would also be the same. Moving or reshaping the area of each cross-section, which each penny represents, doesn't change the volume of the figure as a whole. All right, so hopefully that was helpful to you to help you really visualize what's going on. The last thing we're going to do before you move on to your practice problems is think about an example where we can say these two figures are the same because I know their cross-sectional areas. I haven't labeled these two figures with their side lengths, so I'm going to do that now. I'm going to let you know what the dimensions are. So our first rectangular prism, this is 2 by 2 and has a height of 4. And this triangular prism has a height here of 4, a width of 2, and a height of 4. So what I can do is say, first, I know they have the same height, right? So we know they have the same height. If we can show that they have the same base area, because these are both cylinders and their base area is the same if I shift that base up or down, right? All the cross-sectional areas are the same as the base. If I can show that they have the same base area, then I can say they have the same volume, right? This is my logic. They have the same height, they have the same base area, therefore they have the same volume. And this is how we do this for cylinders. All right, so let's look at our first shape here. We're going to think about our rectangular prism. And how do I find the base area for this rectangle? Well, the area of a rectangle is base times height. My base is 2, my height is 2, so the area here is 2 times 2, which is 4, right? Now let's move on to our triangular prism. I'm telling you that this is a right triangle here. So that means that my base is 2 and my height is 4. My area formula is 1/2 base times height. So that area formula is 1/2 2 times 4. 1/2 of 2 is 1, times 4 is 4. So what that means is that this base area is the same as this base area, which means we have the same volume. So your first set of practice problems is actually matching pictures where you have the same volume. And then your second set of practice problems are some more tricky ones that ask you to think a little bit more. Remember that if you get caught up on any of these things, if you have any questions, to please come to Coach Class and we will help you as best we can. Thank you.